Вот. Ну, как бы в общем случае, да, но это говорит о том, что если у вас есть произвольный элемент x, у него есть разложение Жордана, да, какое-то, то у него, ну, поскольку вы, когда вы возводите в степень n, да, то у вас разложение Жордана возводится в степень n. И, ну, как бы, потому что это полупростой, это унипатентный, они коммутируют. Ну, или что это то же самое, что это гомоморфизм одномерной группы, да, можно сказать, возведение в степень n. Это гомоморфизм одномерной группы в себя. Ну, правда, не всегда понятно, что это включено, ну, в какую-то подгруппу, ну, поэтому лучше так написать. Вот, поэтому вы получаете, что, ну, если вот это равно единице, то поскольку вот это никогда не может быть сократиться с этим, опять же, из-за единственности разложения Жордана, вы получаете, что просто xs в степени n равно единице, ну, ну и вот это равно единице, да, это из единственности. Ну, отсюда следует, что в характеристике 0 xu равно единице, а это элемент как бы, ну, вот ваш элемент остается полупростым. Поэтому, ну, как бы вот все элементы, они как бы являются...
Мы же сразу можем сказать, что просто нет унипатентных элементов.
Ну, как бы, а как? В конечной группе, в смысле? Ну, априори.
Любой элемент там в n степени дает единицу.
Ну да, ну вот я и хотел, вот это и показал, что если бы он был не полупростым, то была бы унипатентная часть, которая бесконечного порядка. Ну, как бы просто я это расписал. Вот.
Унипатентная часть всегда имеет
Бесконечный порядок, но в характеристике не равный нулю. В характеристике P там, ну, многое портится, поэтому... Но это пока, это как раз доказательство, то, что если у вас есть элемент, ну, то унипатентный, то есть если x унипатентный, то тогда он никогда не равен единице в характеристике 0. Извините. Потому что экспонент объективно, ну, это отображение экспонента объективно, ну, как бы ему обратный логарифм. Ну, вот этот элемент вот здесь, он не равен нулю. Да, ну тут у нас пока алгебры нету, у нас просто векторное пространство, но она объективна, ну, на уровне матриц, да. В смысле? Ну-ка, между ну, в смысле, что когда у вас есть унипатентная матрица, то она там объективна. Ну, на матрицы переводят в линейное пространство и наоборот. Ну, одинаковой размерности. Да. Хотя, ну, и тут это отображение алгебраическое, да. Почему для GLN мы это не можем сказать? Просто, ну, хотя потому что у вас ряд бесконечный, поэтому даже, ну, это отображение аналитическое, но не алгебраическое. Это как раз показывает разницу между алгебраической геометрией и группами Ли вот в вещественном контексте. Из-за этого в алгебраической геометрии многое лучше. Хорошо? Все? Ответил? Okay, so on previous class we have discussed the following theorem. So just if you have the set of commuting matrices of commuting matrices can be trigonalized. In a way that all semi-simple matrices here, so all semi-simple matrices of this set are diagonalized, so are diagonal. So whenever you have semi-simple, whenever the matrix is diagonalizable, so can be diagonalized on some basis. So here we find the common basis where all potentially diagonalizable matrices are diagonalizable, and are just diagonal, and the other as triangular matrices. Yeah? So that everything looks like this. And the thing is that why it is important for us, yes, so now we can pick the group. So let us pick the group of commutative group. Then you can trigonalize it. And then you can speak about semi-simple and the unipotent part. Yeah, so so this is the set of unipotent elements. And notice that, so when you notice the following observation, that since just the set of unipotent elements here are just, so this is a subset of now triangular matrices. Yeah, so let me write it down as the separate lemma, because we shall need it later in more general context. So let be proposition. Suppose G is a subgroup of triangular matrices. So triangular matrices. So this is algebraic group. Automatically, if it is subset of in a affine space, it is already affine. Yeah, so it is algebraic group, and you can speak about the set of unipotent elements. So then the set of unipotent elements form the subgroup. Yeah? So the proof is the following. So notice just the evident remark that, so let me do the remark first. Yeah, so if G is not in just arbitrary group, this is not true, of course. Yeah, so then if G is arbitrary, so GU is not a group. I mean, the set of, better to say the set of unipotent elements, because this, just this notation I reserve.
Can you remind, when you say the sum of elements are unipotent?
Meaning that U minus 1 in the n is equal to 0 for some n.
So it's not about a unipotent element in the group, which is different definition, right? That in any representation it will be unipotent.
I mean here, I mean we have proved the equivalence, yeah, of these definitions. Huh?
So if our loop is embedded into a matrix,
Yeah, and so it is if the element is unipotent in the sense of its action on the group algebra, it is unipotent from the viewpoint of the linear group of GLN that you consider. And here, of course, we consider the group in the matrix group, and here you can think of this in as a subgroup of GLV. So the remark and a good exercise that the set of unipotent elements is not a group in general. Yeah, so.
but group when they commute, or just
Hmm?
they form a group when all are triangular but not commutative too.
Yes, so this is, yeah, so this is this proposition, yeah. So precisely I wanted to say, so this is also true in particular case, but we shall need it in more general context. So I plan to do it maybe later, but so it is good time to do it now, I mean. So it is very easy, yes, so because when you are already in, so this is the claim just about triangular matrices, yes, so the element is unipotent, so if G is unipotent, then it is just written as, откройте, да пожалуйста. It is written like this, yes, so you are writing down 1 on the diagonal. It is just a direct check, yes, so that you cannot have something non-trivial on the diagonal, because if you have two matrices with some entries, so of course when you multiply matrices like this, so then you are multiplying the entries. And also notice, yeah, so just I was saying this remark explicitly. Also notice that if you take these elements from the set and you can write, so this is G and this is H. Yeah, so you can write G, H, G inverse, H inverse. Yeah, so notice that this element, so the commutator of these two elements is unipotent element. Yeah, so is unipotent. Yeah, just because the diagonal entries of this, it is lambda mu1, lambda inverse mu inverse. Yeah, so that this is just the product of matrices of lambda 1, lambda n, mu1, etc. mu n, lambda 1 inverse, etc. lambda n inverse, and mu1 inverse, mu n inverse. Yeah? So it is just the remark that we probably need later. And if you have two unipotent elements, so if G and H are unipotent, then the product of the elements of this form is again unipotent. So GH is unipotent. So they form the subgroup, yes, so that means that GU form the subgroup.
Formally speaking, you need to say about inverse elements.
Yes, but formally speaking, yes, so it is clear that if you want to find inverse for triangular matrix, then you are just using again the triangular matrix, because the system of the equations can be, it is just triangular system of equations that can be easily written down. And so this, yeah, so G inverse is unipotent. And so this form a subgroup, yeah? And of course, this form a closed subgroup. So it is closed because you can write down the set of unipotent matrices. So the set of unipotent matrices is isomorphic to the just just can be written in triangular form, triagonalized. Yeah. So can be put in triangular form. Yeah. So can be written as a subset of the set of triangular matrix. And notice that if you have a unipotent matrix, so in general, the set of unipotent matrices in GLN. Yeah, so it is just so to define the unipotent matrix, you just define arbitrary these entries. Yes, so these entries are arbitrary. So there is n minus 1 times n modulo divided by 2 entries. So this set is isomorphic. So there's this number of entries. So the set of unipotent matrices.
Do you say that there is one matrix for all the matrices in the subset, such that the conjugation with this element would lead to
Yes.
representation of the upper diagonal?
Yes, and moreover, the matrices that can be that can be made diagonal on some basis become diagonal. So it is very strong. I mean, from the it is a rather strong condition on the set of matrices. Yeah, so that. Okay. So notice that the set of unipotent matrices are just isomorphic. So this is an algebraic variety. It is unconditional, so you do not need to impose any condition. And as the variety, it is isomorphic to kn minus 1n divided by n. Yeah? So it is the set of unipotent matrices. So let us reserve U for this. Just the definition, since we are not working so far with real forms, so the thing is that so one can confuse this notation with unitary group. Yes, so the group that preserves the Hermitian product, but this is not the case. I mean, so here in algebraic geometry, this thing is not algebraic group, but I mean the set of points. So that's why it is, we do not speak about, just at least in this course, we do not speak about these groups as algebraic groups. Just by definition, the set of unipotent matrices. Yeah, so this is notation. For
the set of unipotent matrices in diagonal?
In triangular, yeah, so the set of triangular unipotent matrices. So this set is just given by specifying entries upstairs and upper diagonal, and you just I mean, so as notice that this is isomorphic, isomorphism as algebraic variety, because of course this has a natural, also a natural structure like additive group structure. Yeah? So the product of additive groups, but this is isomorphism as algebraic varieties. without a group structure. For the evident reason, so the group here is not commutative. Yes, so you see that GU formed a subgroup. It is closed since this set is closed since it is just intersection of the set of G and this unipotent matrices. Yeah? So the set of unipotent matrices. So the reason that when, so a priori when you have arbitrary matrix, it is hard to understand if it is unipotent or not. Yeah, so you have to check something. If it is already written in triangular form, you just know that it is unipotent if and only if it has entries, one entries on the diagonal. Okay? So that is the reason that this is now a subgroup and it is a closed subgroup. Okay? So similarly, when you are speaking about this theorem, so you can speak about the set of semi-simple elements. Inside triangular matrix, inside GLN, yeah? So
it can be treated as triangular matrices with ones on the diagonal.
yes, so I mean when you, so the criterion is the following. So when G is in the triangular form, yeah, so I have to write the claim explicitly. Yeah, so if the element
You could just say that this intersection is after like two specific embeddings. When you intersect G with U and K, this U and K is like embedded via these spaces.
Не, ну в смысле вот это треугольная группа, а это унипотентная. Ну в смысле что? Но они все уже живут в треугольной, то есть как бы надо из них выбрать унипотентный. Yeah, so there is a small claim, but it is easy. So that says that if G belongs to the set of triangular matrices, G is unipotent. If if it is written in the form like this, yeah. So, and the reason is that any element is written like this. So to check that it is unipotent, you have to check, subtract identity matrix and raise it to the power, and of course it is clear. Yeah, so that lambda 1 minus 1 in the power n at least should be 0. Yeah? And the less trivial thing, of course, is to check that this is nilpotent matrices, but we know that so the matrix of this form, this is direct calculation. So if you have 0 entries on the diagonal, so that and downstairs, this is nilpotent. Yeah. So this is direct check. And actually, if you have triangular matrices with lambda I, so it is nilpotent if and only if all entries are 0. Yeah? So that. Yeah, so if you have the matrix like this, yeah, so it is nilpotent if all lambda i's are 0. Yeah, so the important thing is here that you can think of the set, you can see, so you can look at the set of semi-simple elements. And if you look at the set of semi-simple elements, they by the theorem, it is they are diagonalizable. Yes, so by the theorem, they are diagonalizable. So GS is diagonalizable. So this means that simply, so let us denote it by D and K. So here you see that GS is simply is obtained as intersection of G and the set of diagonal matrices. So again, it is a closed algebraic group. Yes, so it is closed algebraic group. So the set of semi-simple elements, yes, so it form again the closed algebraic group, and but this is a rather rare case. I mean, this happens only. I mean, the whole set of diagonal matrices, they of semi-simple elements, they form the group very rarely. So there is another remark, so similar to this one. So in triangular matrices, in T and K, the set of semi-simple elements doesn't form the group. Не, ну как бы, ну в смысле, потому что в треугольном виде у вас может быть, yeah, so the reason for this that in triangular matrices one element can be written like this, and the other element can be written in different bases, and so, huh?
You are saying how there can be not a subgroup, yeah?
Да, ну то есть множество полупростых элементов, я же говорю полупростых, да, то есть не диагональных матрицах в треугольных, а именно полупростых элементов, то есть тех, которые можно сделать в другом базисе диагональными. Yeah, so here I'm speaking about semi-simple elements, so they're not diagonal in the given basis where the matrix is triangular. They can be not diagonal, but potentially in some bases they can be made diagonal. For example, if they have different pairwise different eigenvalues, yes, so they are diagonalizable. Yes, so they are semi-simple, but it can happen that you just multiply these two matrices of this form and get unipotent matrix, for example. Yeah, so if I already gave you, yeah, so I wanted to say it as an exercise, but if you multiply this one by any unipotent matrix, yeah, so that it will have entries again, all different entries, and this will, they are both diagonalizable. Yeah, so this and this one are both diagonalizable. But since their product is unipotent, well, just product with the inverse, then of course it is they do not form the group. Yeah? So so the claim is that in fact G is written as GS times GU, and the reason is that claim.
It's again commutative case.
Yeah, in the commutative case. Yeah. So so this is very specific, but just one of the basic facts. Yeah. So in this case, so your this any element can be written as the product, and clearly, so the reason for this is again Jordan decomposition, because if you have a G inside the algebraic group now, so that you have G is written as GS times GU. So the Jordan decomposition gives you this. So GS belongs to S. So it is this set of diagonal matrices. So GU belongs to GU. So you have the map from the GS times GU that maps surjectively to G. And just in fact, this is, so this map is isomorphism. So it is surjective and injective, so by Jordan decomposition. So this is surjective and injective by Jordan decomposition. Yes, I mean, key in all of this theory, so far let us consider the algebraically closed case. So otherwise the Jordan decomposition doesn't exist even for diagonalizable matrices. Yes, so like over R, you have the rotation matrix. Yes, so that cannot be written as cannot be put in the diagonal form, yeah? Because it doesn't have eigenvectors. Yeah?
But can it be? I read that Jordan decomposition true for all perfect fields. No, so you can write any element as product of semi-simple and uniquely, but maybe not diagonal.
Yes, yes, yeah. So a posteriori when you are, yeah. So this is and this is actually the, yeah. So we can explain this for perfect fields. We can explain this. Yeah. So the reason for yeah. So let us write down this claim. Here, I mean, here, yes. In this theorem, yes. I mean, here I was saying just this proposition was in conditions of the theorem. Yes, so. I mean, just pick a subgroup in the set of matrices. Yeah? So pick algebraic group. So the theorem was about the yeah. So the previous theorem was about the set of matrices. Yes. So if you start with so if you have the set of matrices, the commuting matrices, they can be trigonalized, but it can happen that they do not form the group. Yeah, a priori. But suppose you have additional structure, yes, so that it has the structure of algebraic commutative group. Then you can speak about so we can speak about, I mean even before, but we could speak about the set of unipotent and semi-simple elements. But this allows us, but in the case of commutative algebraic group, this is not only the subsets, the subgroup, but this is also closed algebraic subgroups. Okay?
So in case of commutative group, unipotent and
Algebraic group. In case of group, they are also the groups, yeah. But and in the case of yes, in the case of no, in the case of, so this is a subgroup in the case of when G is just the subset of triangular matrices, yeah. And if G is algebraic group, then it is also closed algebraic subgroup.
So if you have a subset of
Ну, просто если у вас есть подмножество каких-то элементов, они могут образовывать группу, но априори она не обязана быть алгебраической. Ну, как бы, например, вы берете просто конечное число матриц, порождаете ими группу. Тем не менее, ну, как бы утверждение про унипотентность, это скорее утверждение, что они лежат в треугольных, да, что просто это утверждение просто о треугольных матрицах. Да? Что такие, если вот G была группой, то унипотентные элементы в ней образуют подгруппу. Вот. Но если G еще к тому же алгебраическое, то есть замкнутое подмножество по Зарийскому, то эти элементы образуют алгебраическую подгруппу. И то же самое здесь, но только вот это уже при условии, что это коммутативная группа.
Если я беру группу, она лежит в верхнетреугольной, в верхнетреугольных матрицах, то эта группа будет, эта подгруппа будет замкнутой?
Не обязательно, ну как бы.
Пересечение ее с...
Нет, в смысле, если вы берете алгебраическую группу внутри группы треугольных матриц, тогда она будет замкнута.
А если просто группу, то тогда известно, что...
Не, ну вы просто можете взять один унипотентный элемент и породить им группу. Но тогда это будет, он будет дискретный. Да, он в любой степени никогда не даст 0. С другой стороны, значит, их будет бесконечное число, и значит, он никогда не может быть алгебраической группой, да, потому что он просто элемент бесконечного порядка там, ну, в группе. То есть, если бы он образовывал алгебраическую группу, то у вас, ну, над алгебраически замкнутым полем, то у вас бы было там только конечное число элементов. Да, да. Что, в общем...
как-то дальше в тексте? Это, может, я пропустила.
В смысле, вот это?
Ну да, вот это proposition.
Ну, в смысле, ну, как бы вот здесь я это написал. Ну, как бы только для вот этого. Ну, что в этой ситуации это то же самое. Ну, как бы. Не, просто здесь, ну, здесь можно стартовать с алгебраической коммутативной группой, ну, и по теореме мы ее вложили в треугольник. Да, да. Не, ну, более того, мы с вами обсуждали структуру группы, ну, какие могут быть коммутативные связанные алгебраические подгруппы. Вот это вот примерно их описывает структура. Да, ну, что нужно взять унипотентные группы и вот эти. Да, ну, в смысле, вот это so this morphism is just the following. This is just the product. Yeah? Just the product of elements in the group. In the different direction, this is also algebraic. Yeah? Just because in this case, this is precisely why I was explaining this so thoroughly. So just the set to get GS, you can the map on GS. Yes, so the map GS is obtained by, so this is the set of diagonal matrices of diagonal matrices.
So this is just projection.
In G, it is just projection on the set of diagonal matrices. Yes, so you have G, you have a natural quotient G mod U, GU. It is a projection on the set of diagonal matrices.
But taking GU needs like inverses.
Hmm?
But if we want to take unipotent part,
Yes.
it's not a regular function.
Почему? В смысле?
Because we need like to take.
Не, ну в смысле, что они не получаются проекциями, ну как бы...
They are not polynomials.
Нет, они как раз полиномы, ну потому что, ну как бы, потому что есть вот эта проекция, но есть вот эта проекция, она также отождествляется вложением. Ну как бы, so this projection is, I mean, only in this case. It is not what you do in diagonal, in general triangular matrices. Yeah, so here the trick is that this projection, so this quotient is, so this is a subgroup in the set of triangular matrices modular unipotent matrices. Yeah. Okay, it is you just have this kind of map from the set of triangular matrices in the quotient triangular matrices modular unipotent matrices. And here you can pick, you can put it to be pi. Yeah, and here you have G, and you can restrict kernel of pi restriction to G. Yeah, so it is just intersection of G and kernel of pi. So precisely. And we have proved that, so this is the set of unipotent matrices. We have noticed that this is precisely GU. So, and this set is isomorphic to the set of diagonal matrices. But huh?
Isomorphic as algebraic group.
Yes, isomorphic as algebraic group. But notice that, so this means that this subgroup, so this maps to the subgroup of the group of diagonal matrices. But this shows the following, so that if you are thinking about the precisely these elements in GS, so if you think of Jordan decomposition, so if you think of G that it is equal to GS times GU, you notice that if you have this, you realize it as a subgroup here, you can embed, so this is isomorphic to GS, and you can embed, so this is thought as the subgroup of diagonal matrices, and then you can embed this GS back to consider the embedding of GS back to triangle, so you embed it to, yes, to a diagonal matrices. So this you embed this back to G. Yeah?
Yes. So now if I want to take GU, then GU is G times JS inverse.
Yes, I mean
There is inverse. It's not like polynomial.
inverse is polynomial. Taking inverse, it's not 1 over GS. Yeah? So it is picking inverse element. in the group, the taking inverse element is polynomial map. Но G в минус 1 это обратная матрица, да, ну как бы обратная матрица это не единица на что-то, она пишется в полиномиальных координатах.
Сейчас. Не должно быть правдой.
Нет, это совершенно абсолютно правда. Там просто определитель определитель обратим в кольце
So
функции.
we divide by it.
Ну, мы делим на определитель, когда мы пишем обратную матрицу, правильно? Но в алгебре функции на GLV определитель обратим, поэтому это прям... Ну, как
То
бы.
есть функции из GLV регулярные.
Ну, просто пообразующие в функции, so the functions on GLV are generated by the entries and 1 over determinant. But this is a variable.
Because it's a subvariety.
Yes, so you are writing down this as a variable y. I mean, or t.
So inverse map.
So inverse matrix is also polynomial map.
So taking inverse is like regular.
Yes, but not evident thing that this set is just can be put back, and this is precisely isomorphic to the set of all semi-simple elements. Yeah? I mean that appear in this decomposition. This shows that so that this map is at least so this map is bijective. Yeah? So since Jordan decomposition is unique. So that you are writing down G, so explicitly GS times GU. So this gives you that GU times GS maps bijectively to G. Yeah? And so the question, when you take the product, what can be the kernel of this map? And notice that the kernel of phi it is an algebraic group. And it has, if you have a G that belongs to the kernel, I mean, suppose that this product has a kernel. So the problem is that when you have bijective in algebraic geometry, even if you have bijective map on the set of elements, even over algebraically closed field, there are maps which are bijection but not isomorphisms. Yeah? So these are famous Frobenius map. Yes, so the Frobenius map that maps on the set just, for example, on A1 to A1. It maps x to the power pi. Yes, so that this map is bijection, but not so characteristic pi, of course. This is bijection, but not isomorphism. So that's why I'm saying something about, so I want to prove that this is actually isomorphism.
Why isn't the Frobenius isomorphism?
Is bijective?
No, it's bijective, but I don't understand why it isn't an isomorphism.
Ну, потому что, как вы обратный напишете? Ну, Как бы, потому что на алгебре функции он не изоморфизм. So this is not isomorphism. I mean, if you have the map between affine varieties, you have you should have, if you are speaking about isomorphism, this should be isomorphism of the algebra of functions. But if you have the algebra of functions, so k of x here. Да, что это автоморфизм на точках, ну, на алгебраических многообразий. Он автоморфизм на... Вот это да, как раз глупый пример, ну, или умный пример. Вот. Правильно, ну как бы и они биективно отображаются в себя. Но алгебра функций, если вы формально напишете, как действует pullback этого отображения, то это возведение в степень p. Поэтому вы получаете, что, ну как бы... Нет, я просто для p, ну как бы... Это не пример для p равно 3. So if you have a affine space, yeah, so what is... So you take the coordinate and you raise it to pth power. Yeah? So what does it mean from the viewpoint of the map of algebraic variety? Yeah? So that means that suppose you have a coordinate here. Yeah? So you have to understand how to write down the pullback map of this coordinate function. But you evaluate this coordinate function precisely on some point x, yes, here. Yeah? But so this means that you have to evaluate coordinate function. So t is a coordinate function on this factor. So you have to evaluate this coordinate function. This is by definition on the image of this point. Yeah? So this means that you are applying f of x, and the f of x is taking the pth power. So you are evaluating coordinate function at pth power, and the value is just this value. Yeah?
So it's just t of x.
So it's just x of p. Yeah?
And x to the pth power is just
So this means that it embeds. So yeah. So t is just a coordinate function. So this means that from the viewpoint of algebra of functions, the algebra of functions of t maps to the subalgebra formed by x to the power p, which is a subset of k of x. Алгебра функций, ну, афинных многообразий. Да.
Тут, наверное, надо понимать,
Не, ну в смысле, что даже если это морфизм и биекция, то он не обязательно обратим. Да.
x в степени p и x это разные многочлены. Нам тут, кажется, это важно. Несмотря на то, что они как бы одинаковые значения принимают.
Да, ну как бы да. Ну то есть, ну потому что вы их написали по-разному, да, ну как бы.
Поэтому вот.
То есть вы о них думаете как о разных функциях, несмотря на то, что с точки зрения значения не одинаковые,
То есть
да?
вот t от x
Ну,
степени
как
p,
бы.
это же с одной стороны x, с другой стороны мы обязаны это записать
Да.
в каких степени p, потому что, например, композиция многочлена.
Да.
Потому что x это x степени p равно 1. Да ладно.
Не, ну просто это на p точках, да, ну когда вы переходите к...
Мы же на замыкании работаем.
Ну, да.
Ну, на замыкании было понятно, что это все там разные точки.
Но вся наука на алгебраический центр.
Да.
На замкнутых многочлены равны многочлену, тогда же какие?
Да, но здесь ТП имеет больше корней, замыкание.
Да, ну вот, so the problem that this morphism can be bijective, but not separable, but the thing is that you can pick up the kernel.
Подождите,
Ага.
даже в замыкании, типа если мы возьмем FP, там, замкнем, посмотрим отображение афины прямой вот с таким полем, автоморфизмом Фробениуса, оно же все равно не будет алгебраическим. Да? Хотя...
В смысле, алгебраическим-то оно будет, но...
Точнее, обратно алгебраического.
Ну да, не будет, потому что это подмножество функций. Yes, so you had a question or remark? What?
Your projection, the direction of phi is inverse.
So the direction of pi is from G to
Phi there in the middle.
phi. It is just the product. Yeah. So I'm saying that. So here, just I'm taking here G1 and G2, and I'm mapping it to G1 and to G2. But since yeah, so what I meant here that since you have this GU and this is GS, if you take arbitrary G, it can be written as a product of GU and GS. Yeah. So this is unipotent pattern. This is semi-simple, and this product is unique. Yeah. So this is decomposition is unique. So this why this map is bijective on the set of elements. Yeah? So this GU times GS is bijective.
So is there inverse algebraic map from G to G to GS?
Yes, so the reason is for that. So the inverse is written a posteriori, yes, so that you map G to G times U, yeah? Okay, and then this is isomorphic to GS. And you embed this in the set of diagonal matrices. And this embeds GS to G. Yeah? So this allows you to, so if you have this map, so let us put this projection to be pi. So this allows to write down GU is the element of pi inverse. So you apply, you have now the map from G to GU. So the most complicated map here is how to construct this map from G to GU. And this is constructed via the following map. So you take element G, and you can take G inverse of phi times, so pi of G inverse times U, G. So this is unipotent element. So this is unipotent. And since the group of is commutative, it is also homomorphic. So you have the maps between. So this allows you to write down that you have the map from. So you have the. You can directly write down the map from GU times GS to G, and then you can map it back to GU times GS. And this is identity. Okay. Also, you may check it. The thing is, the only thing is here that it is not. In this setting, it's not very clear that it is identity map. So I wanted to just modify it a little bit and to say the following. So suppose this map has a kernel. So this is homomorphism of algebraic groups. Yeah. So you can pick up kernel of phi. This is algebraic subgroup. Yeah. So algebraic group. So suppose some element G. So it has elements over algebraic closure. Yeah? So if it is non-trivial, then since we are working over algebraic closure, there exists G which is non-trivial element. So G is not equal to E. And this implies, so this G, I mean this G tilde, yeah? So this G tilde is written as GU times GS. But from the viewpoint of the kernel, these are those elements that maps to 0. Yeah? So this is GU times GS is equal to identity. So this implies that GU and GS is equal to 0, to identity. So, and similarly, you do the same. You take the element which maps here, and so you see that it can map to 0 only if it is, so if it is, it's unipotent and unipotent and semi-simple part is 0. Yeah? So again, you consider kernel of phi tilde, and G maps to. So our mapping is constructed that G maps to unipotent and semi-simple part. So this means that if this is 0 identity, then G is of course 0. Trivial element. Yeah. So this shows that this decomposition is bijection. And there was very good question about Jordan decomposition. So if it is that it holds over the perfect fields.
What is the perfect field?
Such that K is equal to the power of P, pth power. Okay? Yeah.
Okay.
So this is called perfect field. Yeah.
What is when O exists of power P?
Yeah.
Just one particular P. It would be perfect P.
Yeah. So well, it exists only in characteristics P, and so a perfect field, it is either the field of characteristic 0 or in characteristic P it is. So this is a characteristic 0 unconditionally, so there is no, so P is equal to infinity. So I mean, so if characteristic is 0, so this is not a condition, so this is unconditional, or characteristic is P. Yeah? So in this case, then the claim is that then Jordan decomposition exists. And the reason for that is that if you have G, so the element that, so if you have a perfect field, yeah, so if you have G which is defined over K, yeah, so that K can be embedded in its algebraic closure. And so over K bar, you have decomposition G belongs to GS times GU. And this means that GS and GU has entries in, so that they consist of finite collection of entries. So they have entries in some finitely generated field. So you can speak about, so E can be put in the Galois extension. So E is some E tilde, it is Galois extension. So, and when you're speaking about Galois extension,
Since Galois is French, it should be Galois, maybe.
Galois. Нет, ну, Galois произносится. Galois. Ну,
Sorry, that's not. Just continue.
Yeah, so, yeah, so if you have Galois extension, extension Galois, ну, короче говоря, что если у нас есть, so if you have a Galois extension, then you can check when the elements belong to your field. Yes, so your element X belong to to the set of points of here I will write the set of points over K, meaning that it is the subset, for example, of matrices with entries in K. Yeah, so which is the subset of matrices with entries in K bar. Yeah, so to check that X belongs to K, this is if and only if. You take X and you apply automorphism, and it is equal to X. Yes, so that you have, if you have matrix, then you can apply. So for the matrix, of course, I mean the following thing, that X is written as the matrix Aij. So simply for X sigma, I mean that I apply sigma, the Galois automorphism, to the entries of matrices. And if you have this kind of property, then of course to check that something, that the matrix belongs to the matrix in entries in the values of K, yes, so that entries belongs to K. This happens if and only if the application of sigma to X is equal to X. So if you have this equality, so for any sigma, of course, yes, so for any sigma in the Galois group. So then if you have this decomposition, so you can write it down over K bar. So so here we're writing down over E tilde. So now we have to check that this decomposition belongs to, or this GS and GU belongs to the matrices with entries in E tilde. So you apply sigma of G. This is the same element because we started with G that has entries in K. And this is equal to sigma of GS times sigma of GU. And by the what you have to check, that if you apply automorphism of the field, so this is semi-simple element, and because it is just changing the entries by automorphism. Yeah, so this is just in some basis if G is written like this. Yes, so that sigma of G is written by like this. Yes, so just by sigma of lambda.
Well,
And
maybe we cannot diagonalize if E is not closed, but maybe it follows from our.
I mean, no. If you have already this decomposition over K bar, then the matrices has entries in K bar, but they have finite collection of entries, so you can put them in Galois extension. I mean, you can put it in the finitely generated subfield. Then since the field is perfect, you can embed it in the Galo extension just by adding all roots.
Yes, yes. But why we can diagonalize our simple part over E?
Так я же давайте я вам по-русски объясню. Но вы взяли над К с чертой, но над расширением. Разложили вот это, в диагональ, в произведение вот этого элемента и вот этого. А как мы раскладываем в GLV? Мы его диагонализуем. Вот это вот разложение написано в GLV, значит оно как бы...
Сейчас, но они же сами не обязательно
да, я понял вас. Вы правы в смысле, что что мы диагонализуем его уже вот в этой записи. То есть мы думаем об этом как о элементе GLNK с чертой, но здесь мы его диагонализуем. Да? Уже сразу, до того, как писать вот это разложение. Да, то есть как бы вы правы, да, что просто... я все-таки, когда сам для себя думаю о Жордановом разложении, то я тут же, я все-таки его привожу к диагональному виду, поэтому, как бы в терминах линейной алгебры. Yeah, so when I think myself of Jordan decomposition, of course I think of GS of diagonal matrix. So that's why just from the beginning, since we are working over algebraically closed field, we are writing down this decomposition as decomposition here, where this is already diagonal. Okay? Of the what? So this is unrelated with this. I'm just saying that Jordan decomposition is defined over the perfect field. So in order to define this Jordan decomposition, I need to check that this element and this one is fixed under the action of x, yeah? Of sigma. And since it is, so you take this element, so it is potential, this is, so you see that if you apply sigma to GS, then it also can be diagonalized, but probably over k bar. Yeah. So, but anyway, this condition of being diagonalizable, it preserves when you change the sigma, because so if GS is diagonalizable in the basis V1 Vn, so meaning that GS Vi is equal to lambda I Vi, then of course sigma of GS is diagonalizable in the basis sigma of Vi, sigma of lambda I and sigma of Vi. So of course, so this is, I do not say that GS and G are diagonalized on the same basis, yeah, but I do not need it. So you have, so you know that this is diagonalizable. So this is semi-simple. And this is still unipotent. So you can think of this over E tilde over K bar, and in the end you see that. So then by uniqueness over K bar, so you see that this is the same element, so GS is equal to sigma of GS for any sigma, and GU is equal to sigma of GU.
Вы хотите сказать так, что мы сначала вот как бы
Ну, вам даже не, ну,
поднимаем, потом там говорим, что не диагонализуется, потом опять опускаем.
не, ну вам не надо диагонализовать вот в этом разложении. Вам нужно только что знать, что оно единственное. Ну, как бы, в принципе, да. То есть вам даже не надо знать, что оно здесь диагонально. То есть мы просто, ну, это следствие именно, что вот это единственность разложения, что тип сохраняется, да, то есть быть диагонализуемым сохраняется при действии автоморфизма поля, и быть, быть унипотентным тоже сохраняется. Ну, and of course, one should notice that this is also yeah, so here one shouldn't even know that this element is the same element as I mean that this is an element of the same subgroup. Yeah, so just.
This perfect figures without the FP fields.
Нет, ну как бы это, ну, они не обязательно конечные. Но вы можете просто формально присоединить корень по этой степени ко всем элементам. Окей?
Просто тут пишут, что perfect field это когда Frobenius это автоморфизм, а у эксперта минус x это максимум.
Но если оно нет, ну нет, вы же не xpt в минус x. Это вы неподвижные точки Фробениуса смотрите. А вы извлекаете из А, из элемента А. Окей, so yeah, so it's good time to make a break, yeah? Или мы уже что-то перетянули? Я что-то со временем не соображу. Мы...
Сейчас 13:02, это мы...
А заканчиваем когда?
14:20.
14:20. Вот. Ну, давайте сейчас перерыв сделаем. Да? Yeah, so it is a good logical point to make a break now.